All right, we're going to show that the alpha is dependent upon the radius of the disk, but the ACOM, the linear acceleration, is not. So if we look at the acceleration about the center of mass, if we solve Newton's second law for rotational motion, we know that alpha is torque over moment of inertia. And about the center of mass, the moment of inertia of a disk is 1/2 mr squared. The torque is the force times the lever arm distance. So since we're doing it about the center of mass, all these forces, the normal force and the weight, act through the center of mass, so they produce no torque. Frictional force, Fs, is the only force that has a line of action that is not through the center of mass. So that is perpendicular to the lever arm distance, so the torque then is just the frictional force times the radius. And even though the frictional force is unknown, we can still see from this equation that alpha is dependent upon the radius. However, we won't be able to calculate this since we don't know what the frictional force is. So I went ahead and did it about point P. That's the point where the disk is in contact with the ramp. And now my force that causes rotation or torque is the weight times the sine of theta. So that here's my weight vector. This is the component of the weight that is perpendicular to my lever arm distance. So now my torque is the weight times sine theta times r. And the moment of inertia now, don't forget we have to use the parallel axis theorem because we're rotating about point P, not through the center of mass. So that combines to be 1.5 mr squared. The m's cancel, one of the r's cancel, and I'm left with alpha is this expression. Once again, we see that it is dependent upon the radius. The acceleration at the center of mass, which is the same as the tangential acceleration, we know is r times alpha. So when I multiply this expression times r, the r's cancel out, and I'm left with an expression that you see does not have r in it. So that tells me that the ACOM is independent of the radius of the disk. Now we're going to show that the ratio of the angular acceleration of the hoop over the angular acceleration of the disk is 0.75. It asks you to calculate that. This is what you should get. How do we go about that? Well, there's two ways to do it. The first way is to use the equation on page 280, equation 1110, and plug in the ICOM for a disk and the ICOM for a hoop, and 1/2 mr squared or mr squared, and the mr squared in both cases cancel out. And this is what we're left here for the disk and the hoop. So then you make that ratio and you see it simplifies to 0.75. We initially get the ratio of the linear accelerations, and we know that linear acceleration is r times angular acceleration. So the ratio is the same, 0.75. Or another way you could do it is to use this figure again and equation 1044, which says torque is equal to force times moment arm. So here is our perpendicular force, mg sine theta. Here's our moment arm r. So that's our torque. And we know that the mass of the hoop and the disk are the same. G is the same, of course, for both. They're on the same incline, so theta is the same. The radius of the hoop and the disk are the same. So all these variables are the same for both the hoop and the disk. So if their torques are equal, then I know torque is equal to I alpha. So their I times alpha of both the hoop and the disk must be equal as well. So we're just going to rearrange this to solve for alpha hoop over alpha disk. But we have to make sure we use the parallel axis theorem. So the moment of inertia of the hoop and the moment of inertia of the disk about our axis of rotation right here, point P. When we rearrange it, we get 1.5 over 2, which is 0.75. The same thing we got doing it this way. Is energy conserved in this experiment? Compare the gravitational potential energy at the top to the total kinetic energy at the bottom. So here is my value for G. Here is my mass of both the disk and the hoop. They're close enough that I just called them both 640 grams. And so my potential energy for both the hoop and the disc, using a height I figured out from the diagram, was 46 centimeters. So MGH for both the hoop and the disc is 2.89 joules. Then over here, you can see I calculated the translational kinetic energy at the bottom, which is 1/2 mv squared for the disc and the hoop. And the rotational kinetic energy is 1/2 I omega squared. Here are my values for ICOM for the disc and the hoop. So I calculate those and I add them together to give me the total kinetic energy at the bottom of the ramp, which is the sum of these two, rotational plus translational. You can also think of it as the purely rotational kinetic energy using 1/2 I omega squared, where I is now I about point P, the point at which the disc or the hoop is in contact with the ramp. Either way, you see that we get numbers that are significantly larger than the potential energy at the top. So the question is, how come? We know that energy is always conserved, and this is not displaying that. There must be some error somewhere. And to hypothesize on what the error is one thing, but to actually figure out if that is a legitimate source of error is another thing. To say, oh, it's friction, or oh, it's air resistance. Well, okay, analyze it. How does air resistance affect the situation? How does friction affect the situation? How does anything that you list as a source of error affect the situation? And does it make sense that that could be a possible reason for this discrepancy in the energies? Okay, so when we look at what sources of error we could have and how they affect our results, let's look at some of the common answers that I got from students in the lab. The most common one was, we're only able to measure the time in tenths of seconds. And I suggested that you use a frame-by-frame approach because the video is taken at 30 frames per second. So that way we can get
frame by frame, we can get granularity of 1/30th of a second.
So let me show you what I mean here. So I mentioned in the lab instructions that you can go frame by frame in the video. So you see here as I hit the forward and back button, I can go through the video one frame at a time. And here we go. If I go 1, there's the start of 1.3 seconds. So 1, 2, 3. Now I'm at 1.4 seconds. 1, 2, 3. Now I'm at 1.5 seconds. So there are 3 frames per second. So each frame is 1/3 of a second. So I can get basically 1/3 of a second granularity here. So looking at the disc, the brown disc, there we go. It's rolling off the end of the ramp right there. So and the very next frame, so it's 1.4, 1.5, and 1/3, and 2/3, and it's a little bit off. So let's go with 1.55 seconds for the disc, and then for the hoop, there we go. It rolls off. There's 1.7. The next frame is 1.8, and it's already off. So 1.7. So I'm going to go with 1.77. If we only had granularity to tenths of a second, that means for the disc, we might guess 1.6. And there you can see that's a significant distance that it's moved in that time, now that it's at 1.6. So that's quite a large error. And for the disc, if we said 1.8, that's where it's at. Not quite as bad, but still, you can see with the 1/3 of a second granularity on the frames, we can get a much more accurate time. Let's go to our data sheet now, and let's try 1.6 and 1.8. And you can see when we do that, it did bring the kinetic energy down a little bit, but it's still a significant difference. And so the time is not really a major source of error when we have the ability to record the time as well as we can with the video. Another common answer I saw was, we did not account for air resistance. Well, let's think about that for a minute. First of all, at very low speeds and for very heavy objects, air does not make much of a difference. It's pretty negligible. But what if it was significant? Well, air resistance, we know, takes kinetic energy away from an object and converts that kinetic energy to thermal energy. And that's not what we're seeing here. Put it this way, if there was no air resistance, there would be even more kinetic energy, and it would be even a larger discrepancy where the PE would be far less than the KE. So in other words, the air resistance is not the reason for the discrepancy. Another common answer I got for sources of error were friction, non-uniform density, and maybe the wheels are slipping on the ramp. Well, all three of these factors do affect the amount that the wheel rotates. But if you think about the friction, there can't be too much friction. The more friction there is, that just means it guarantees that the wheel won't slip. If you remember, the static frictional force usually is not going to be the maximum static frictional force. It's just the static frictional force. Also, if there's not enough friction, then that's when the wheel will slide or slip. But the only effect that has is that it's going to change the ratio of the rotational kinetic energy to the translational kinetic energy. Remember, the total kinetic energy is the sum of those two, and that should still be equal to the potential energy at the top, even if it does slip. Same thing goes for non-uniform density. If you think about the disk, that is uniform density, but the hoop is very non-uniform density. It's metal around the edges and air on the inside. So anything that's non-uniform density is just something that has a different moment of inertia than the disk that has uniform density, just like the hoop has a different moment of inertia than the disk because its distribution of mass is different. Remember, that's basically what the moment of inertia is a measure of, the distribution of the mass. So here are the calculations that I show for the disk about the center of mass. The kinetic energy is the sum of the translational kinetic energy plus the rotational kinetic energy. And when I change omega to V over R and insert 1/2 mr squared for a disk about its center of mass for moment of inertia, I simplify the equation down to this, and you can see that the total kinetic energy is this term plus this term, and this is 1/2 of this amount. So in other words, of all of the kinetic energy, this part right here, which is the rotational, is 1/3 or 33%, right? Half of this 33 is half of 33.33 is half of 66.66. And then for the hoop, the moment of inertia is just mr squared, not 1/2 mr squared. And when you do the same analysis, you see that the translational is 1/2 mv squared, the rotational is 1/2 mv squared, so it's half and half. So you get half translational and half rotational for the hoop, and
1/3 rotational and 2/3 translational for the disk.
And any other objects that have different moments of inertia, which would be due to their non-uniform density, would just yield a different split in the percentage. But the total amount should still be the same as the potential energy. Remember, conservation of energy is a steadfast rule. So we've looked at a long list of possible errors that could account for the discrepancy we see in the kinetic energy being more than the potential energy. And we haven't really found a good source of that error. But there is one thing we haven't looked at yet, and that's the potential energy. So how did we figure out the potential energy before? Well, we saw that the top of the ramp was at approximately 50 centimeters. The bottom of the ramp was approximately 4 centimeters. So the delta H from the top to the bottom is 50 minus 4, or 46 centimeters. And that is logical reasoning. But since we can't seem to find the source of error anywhere else, we have to draw our attention to this and suspect something may be up with it. So as I was looking at my setup, something struck my eye, and that's this board on my fence back here. If you see this board on my fence, you see that it's bent basically. And so that said to me, oh, and then I see these cracks. Well, this crack has always been here. That's the groove in the patio. But there's also some other cracks in my patio that you can't really see in this picture. But it made me suspect perhaps this end is lower than this end of the door by more than 46 centimeters, because perhaps my patio is slanted. So what I did was I got out my level and I put it on the patio, and sure enough, the level tells me my patio is not perfectly flat. It's not level with respect to gravity. So what I did was I did this setup where I made a right triangle. You can see the right triangle here with the level, and I made sure now that this is level. And what this is going to be able to tell me is I'll measure this height and this hypotenuse. I could have measured the length of the level as well. Any two sides of the triangle. Now, since it is a right triangle, this meter stick, I hung it from the top edge and let gravity pull it straight down. So I know this meter stick is vertical, and I know the level is horizontal by the bubble marker. And so now I know this is a right triangle. And I see that by using the sides of the triangle, I can figure out that the angle of incline here of the door is 14.7 degrees. I think you would find if you use the old numbers with 46 centimeters, that gave you an angle of 13.3 degrees. But now because the ground is tilted, I have to correct for the unlevel ground. Now my whole setup is tilted, and you can see I've kept that same black triangle, but I've tilted it now so that the bottom of the ramp is a little lower than before. And now using the pink triangle, I can and knowing that the angle of incline is 14.7 degrees, I can see that the delta H of the wheels are actually about 51 centimeters and not 46 centimeters. So now that I know that, I made a table with all the calculations you were asked to do. I chose a random student's data that said the time for the disc was 1.517 and the time for the hoop is 1.733, and the height was 46 centimeters. And these were pretty typical results here. The ratio of the alphas was 0.77 instead of 0.75, which was a 2.1% difference. And here are our percent differences for the KE and the PE. There you go. And now that we know our new delta H, I made a new table. In my new table, I've added another row that allows me to adjust the height and the time and redo the calculations. So here you can see I've adjusted the height by 5 centimeters as we determined with the level to make the delta H now 51 centimeters. And over here, these two bold font boxes allow me to adjust the time. So you can see here, the original time was 1.517. If I add a third of a tenth of a second, which is one frame, there we go, 0.033, 1.517 changes to 1.55. So I can pick the adjusted times for both the disc and the hoop. And what I'm trying to show you here is that within our measurement error, do our laws of physics hold true? And so what I've said to myself is, I think I can measure the time within one frame of the video, but I have to account for the start of the time measurement and the end of the time measurement. So that's a time measurement error window of plus or minus 2 video frames, one at the start and one at the end. So 2 frames is 0.066 seconds. So in other words, if I can adjust the time by less than 0.066 seconds, my experiment verifies the laws of physics. So here we go. Within my time error window of 0.066 seconds, I've adjusted both of these to less than that, and my new height. And you can see I get a perfect agreement between potential and kinetic energy and the perfect value for the ratio of the alphas. How did I come up with these numbers? Well, I just messed around with them until I saw these go to 0, and then I checked to make sure they were within my error window. Ta-da!